Imagine you just spent $5 million on a state-of-the-art manufacturing robot.
Right, which is a massive investment for any facility.
Oh, totally. And it is an absolute marvel of modern engineering, you know. It's capable of carving solid titanium with microscopic precision, but right now, it is sitting completely dead.
Just literally doing nothing.
Doing nothing. Yeah. Because a human operator is taking 5 full minutes to manually unscrew, clean, and retighten a giant metal clamp.
And you are bleeding thousands of dollars an hour when that happens.
Exactly. Entirely. Because your spindle, the part of the machine that actually does the cutting, is just waiting around for a human being. So welcome to another deep dive. You are the third person in our conversation today, and we are stepping right onto the factory floor to solve a multi-million-dollar bottleneck.
Yeah, we are looking at the critical piece of the puzzle that dictates whether an industrial facility actually turns a profit. We're exploring the ultimate showdown in how horizontal machining centers handle the metal they cut.
Right, the automatic pallet changer versus the stationary table.
Exactly. And the financial stakes attached to this one specific engineering choice are, well, they're massive.
Okay, let's unpack this setup. If you are managing a high-volume factory floor right now, the word idle is essentially a curse word.
Oh, 100%. It's the enemy.
Yeah, and we are trying to figure out how the most advanced manufacturing plants in the world eliminate that idle threat. Because the pure mathematical pain of manual loading on a stationary table is just brutal.
It really is.
I mean, the operator's routine requires pulling open these heavy cabin doors, physically loosening the clamps on a finished part, hauling it out, and this is the worst part, painstakingly blowing away all the corrosive coolant and sharp metal chips.
Right, you have to get it completely clean.
Yeah, and only then do they hoist a new chunk of raw material inside, dial in the alignment, and torque everything down.
And that whole process routinely eats up 3 to 5 full minutes.
Which feels like an eternity in manufacturing.
It is an eternity. During that entire window, the machine's computer is on, the lights are on, you are paying the operator's hourly wage, but the cutting tool itself is completely motionless.
And in the world of industrial economics, if the spindle isn't cutting, you aren't making money.
Exactly. That is the fundamental problem. The automatic pallet changer, or APC as it's called, was invented to solve through basically the genius of parallel processing.
So you essentially split the workspace into 2 distinct worlds, right? Like the inside and the outside.
That's a great way to look at it. A dual-station APC completely separates the cutting environment from the loading environment. While the machine is sealed inside its cabin, aggressively throwing sparks and cutting part A, the human operator is standing safely outside in a quiet, dry area.
Oh, nice.
Yeah, so they can take their absolute time unclamping the previous part and loading part B onto a secondary pallet. The preparation happens simultaneously with the production.
So there's no waiting.
Right. When the machine finishes cutting part A, the doors slide open, and an automated mechanism simply rotates or shuttles the 2 pallets. The finished metal comes out, the raw metal goes in.
And the actual time savings on that swap are staggering. I mean, looking at our sources, an APC completes that entire physical exchange in anywhere from 12.5 to 45 seconds.
It's incredibly fast.
You take the spindle's idle time and instantly crush it by up to 93% compared to a manual table.
Which is huge for the bottom line. The overall machine utilization rate, the metric that tracks how often that machine is actively generating value, usually hovers under 60% with a manual setup.
Right.
But with an APC, it skyrockets past 80%.
Wow. And we see the real-world application of this vividly in new energy vehicle factories, right?
Oh, absolutely. Those EV facilities are tasked with churning out thousands of complex aluminum battery housings and car body components every single day.
Just nonstop volume.
Oh, nonstop. For high-volume recurring jobs, the APC becomes a non-negotiable piece of equipment. The labor cost per part drops drastically because the synchronization is flawless. The operator never waits on the machine, and the machine never waits on the operator.
Think of it like a Formula One pit stop.
Oh, I like that.
Right? Using a manual stationary table is like pulling your race car over to the side of the track, turning off the engine, getting out, jacking up the car yourself, changing your own tires, and pumping your own gas while the race clock just keeps running.
Which would be an awful strategy for a race.
Exactly. The APC is the coordinated pit crew. The tires are waiting, the fuel hose is primed, and the moment the car pulls into the box, boom, 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 everything swaps in seconds.
And the spindle, just like the F1 car, barely registers the pause before it is back at top speed.
Yeah, that continuous motion model is basically the holy grail of mass production. Maximizing continuous motion changes the entire financial trajectory of a factory.
It completely rewrites the math.
But wait, if the APC is basically a magic wand for printing profit, why wouldn't every single factory on Earth just buy one?
That's the logical next question.
Right, like why not just build a bigger, beefier APC for everything? Even for, say, a massive 10-ton ship engine. Just scale up the servo motors and make the slide rails thicker. Why regress to a manual stationary table at all?
Well, because physics doesn't scale linearly.
Oh, interesting.
Yeah, speed always demands a structural compromise. An APC achieves that 15-second swap because it relies on a highly complex articulated system underneath the pallet.
Okay, so lots of moving parts.
Exactly. We are talking about moving gears, hydraulic lifts, delicate slide rails, and electrical servo motors. When you try to place a 10-ton iron casting, something the size of a small house, onto an articulated system, you run headfirst into the limits of material strength.
The sheer mass simply crushes the automation.
Completely. Putting a 10-ton block of steel onto a delicate set of exchange rails would cause immediate, catastrophic fatigue failure.
Wow. So the steel rails themselves would just physically bow under the localized pressure?
They would bow, they would snap, and the servo motors would basically incinerate their own wiring trying to shuttle that kind of weight around.
Okay, I see.
Think about moving a massive double-door refrigerator. If you try to rest that refrigerator on a skateboard to move it quickly, the skateboard's trucks are going to snap, the wheels will shatter, and the fridge is going crashing to the floor.
That is a disaster waiting to happen.
Right. But if you set that same refrigerator down on a solid concrete slab, it sits perfectly stable forever. That is why the stationary table absolutely triumphs in heavy manufacturing.
So a stationary table is basically that concrete slab.
Exactly.
It is an integrated, solid cast iron bed mounted directly to the bedrock foundation of the machine itself. There are absolutely zero moving exchange mechanisms underneath it.
None. And because it sits on that solid iron foundation, a stationary table offers unmatched structural rigidity.
Which you need for heavy cutting.
Oh, yeah. When a cutting tool digs into a massive block of steel, it generates violent, aggressive vibrations. A stationary table absorbs those forces without flinching.
Right.
Furthermore, it offers a crucial setup advantage. With a giant part, the stationary table allows the operator to use an overhead factory crane to carefully lower a massive casting onto the bed just one time. You clamp it down securely, and you perform multi-sided machining in one single, unmoving setup.
If we connect this to the bigger picture, it all comes down to microscopic error, doesn't it?
That's exactly it.
Because anytime you move a workpiece, even by an inch, you introduce the mathematical risk of misalignment. When you are dealing with a one-off giant mold for an airplane wing, the forces are immense.
And the stakes are astronomically high.
Right. If the table shifts or vibrates even a fraction of a millimeter because it is sitting on a moving APC rail, the entire multi-million-dollar part is ruined. Eliminating movement is the only way to guarantee absolute structural integrity.
And the concept of microscopic error doesn't just haunt 10-ton ship engines. Even if you are cutting lightweight, 1-pound parts that an APC can toss around effortlessly, moving the workpiece creates a terrifying precision problem.
Here's where it gets really interesting. In high-end machining, controlling where the part sits after a move is called repeat positioning accuracy.
Yes.
Let's follow the journey of a single pallet on an APC to understand this. You cut the front side of a part. The automated changer shuttles the pallet outside so the operator can unclamp the metal, flip it over, and clamp it back down.
Simple enough so far.
Right. Then the APC shuttles that pallet back inside the machine to cut the backside. When that pallet drops back into the cutting zone, it must lock into the exact same spatial coordinates it held 5 minutes ago.
And exact in this context is almost hard to comprehend. Top-tier ATCs are required to achieve a repeat positioning accuracy within 0.0005 millimeters.
Wait, 0.0005 millimeters. To put that abstract number into perspective for you listening, a standard human hair is about 0.07 millimeters thick.
Yeah, it's wild.
You are locking a heavy metal pallet loaded with clamps and raw steel into a mechanical base with an accuracy that is roughly 1/14 the width of a human hair.
Achieving that physical feat requires brilliant geometry. High-quality automated changers rely on precision taper cones.
Okay, picture a steep metal funnel.
Right. As the heavy pallet lowers down into the machine, it features female receivers that slot directly onto these male taper cones. Because the sides of a cone are sloped, it doesn't matter if the pallet is initially misaligned by a millimeter or two.
Oh, I see.
As gravity and hydraulic clamping pressure pull the pallet downward, the sloped walls physically force the pallet to slide down into the absolute dead center microscopic position. It mechanically self-corrects.
That is genius. But wait, you are performing this fraction of a hair alignment inside a sealed box filled with flying metal shards, grease, and high-pressure corrosive liquid.
Yeah, the worst environment imaginable.
How does a rogue piece of metal not just get trapped under the pallet and ruin the alignment?
Well, that is the constant threat. To fight it, the machine utilizes automated high-pressure air blasts.
Oh, wow.
Yeah, right before the pallet makes contact with the taper cones, jet nozzles fire a hurricane of compressed air across the mating surfaces to aggressively clear away any metal chips or dirty coolant.
Because if the air blast misses a single microscopic metal shaving and it gets pinned between the pallet and the cone, the base position shifts.
And the naked human eye cannot possibly detect a 0.01 millimeter tilt.
So wait, does the machine know it's misaligned? Or does it just blindly follow its programming and start cutting better anyway?
It cuts blindly. The machine's computer operates under the strict assumption that the metal is at position 0. If a tracked metal chip tilts the pallet to position 0.01, the cutting tool executes its exact programmed path relative to a crooked piece of metal.
Oh no.
This completely destroys multi-sided accuracy.
We need to define exactly what happens to the geometry of the part here, because the terminology in our sources can get dense. Engineers talk about failing perpendicularity and coaxiality inspections.
Let's break those down because they're critical. Failing perpendicularity means a feature that was supposed to be a mathematically perfect 90-degree corner is suddenly 89.9 degrees, all because the pallet was sitting on a tiny speck of debris.
That sounds bad, but coaxiality sounds even worse.
Failing coaxiality is definitely worse for complex assemblies. Imagine drilling a deep hole straight through a thick block of engine casing.
Okay.
If the pallet is microscopically tilted, that drill bit enters the front of the block perfectly. But as it travels through the metal at a slight angle, the error magnifies. By the time the drill exits the back of the part, the hole is completely out of position.
The mounting bolts won't fit.
Exactly.
Transmission gears won't mesh. In a mass production environment, this is a catastrophe. Your dimensional dispersion, basically the variation from part to part, goes wild.
It ruins the whole batch.
Suddenly your factory scrap rate skyrockets and you are throwing away thousands of dollars of expensive raw aluminum and wasting precious machine time.
And for industries like aerospace, this level of precision is utterly non-negotiable.
Absolutely. If you are machining structural components for an airplane wing or complex titanium turbine blades for a jet engine, a microscopic misalignment caused by a dirty APC taper cone can lead to disastrous aerodynamic failures.
This raises an important question about the hidden tax of advanced automation. You are locking a part down with unimaginable precision inside a violently dirty environment.
Yeah, how do you even do that?
Well, how do you keep an APC functioning perfectly without it tearing itself apart?
You pay for it in maintenance. Factory maintenance teams spend roughly 80% of their time fixing and troubleshooting automated systems. 80%.
It's a staggering number. An APC is an incredibly dense package of sensitive components. You are dealing with complex electrical servo drives, delicate pneumatic locking pins, arc clamps, limit switches, and layers of automation software constantly talking to the main computer.
It requires an exhausting level of preventative babysitting. Maintenance technicians have to routinely break out laser trackers just to recalibrate the precise exchange alignment.
It's highly skilled work.
They must perform complex air tightness tests on the locking mechanisms just to ensure the internal seals haven't degraded. It is a never-ending battle to protect the sensitive guide rails from the dirty coolant.
Because if just one tiny piece of hardened metal chip manages to bypass a rubber seal and wedge itself into a locking pin, the entire automated changer jams solid.
And when an APC jams, it is never a quick 10-minute fix.
Never. You need highly specialized technicians who can troubleshoot mechanical binding, electrical faults, and software errors all simultaneously.
That sounds like a nightmare.
They often have to dismantle the precision alignment system, clean the debris, replace the ruined seals, rebuild the mechanism, and then painstakingly recalibrate the entire assembly back to that 0.005 millimeter tolerance.
So what does this all mean for the person actually running the factory floor? Contrast that multi-day repair nightmare with the absolute boring simplicity of a stationary table.
The contrast is night and day. A stationary table has zero moving exchange mechanisms to jam. There is no automation software to crash in the middle of the cycle. There are no servo motors to burn out under a heavy load. There are no taper cones requiring high-pressure air blasts.
The maintenance routine for a stationary table basically involves an operator wiping down the flat cast iron surface with a rag, tightening the heavy bolts holding the part, and occasionally adding a few drops of simple lubricating oil to the guideways.
It's wonderfully low-tech, and because of that rugged simplicity, the failure rate of a stationary table remains near zero for decades.
Wow, decades.
Decades. Which brings up the total cost of ownership. The APC buys you incredible production efficiency on paper. Gaining an extra 20 to 30% of spindle uptime sounds like an automatic win.
It really does.
But you pay for that speed up front in the purchase price, and you pay for it continuously with complex, highly skilled maintenance demands.
It is a brutal risk versus reward calculation. Let's say your new APC saves you 3 minutes of idle time on every single aluminum bracket you produce. You feel like an absolute genius, right? The machine is practically printing money.
You feel unstoppable.
But 3 months later, a tiny sliver of metal slips past a degraded seal. The locking pin seizes, and the pallet changer freezes halfway through a swap.
And everything grinds to a halt.
It takes your specialized repair tech 2 full days to diagnose, dismantle, rebuild, and recalibrate the system. During those 48 hours, your $5 million horizontal machining center is completely dead. Have those 3-minute savings actually put you ahead of the factory next door using a reliable manual table?
Well, if you are running a high-volume shop producing thousands of identical car parts and your preventative maintenance team is world-class, the math says you are still ahead.
Okay, so volume is key.
Yeah, the sheer volume makes up for the occasional downtime. But if your maintenance team is already stretched incredibly thin, or you are running a high-mix, low-volume shop making a dozen different heavy parts a day, that highly strung APC will quickly become your worst financial nightmare.
It completely reframes how you look at factory automation. We tend to assume robots equal faster, therefore robots equal better.
It's a common trap.
But it is actually a delicate, stressful ecosystem. Balancing speed, extreme physical weight, microscopic precision, and exhausting upkeep.
It requires a profound understanding of the specific economic reality of your own factory floor. There is no universal right answer, only the right tool for the right job.
So let's bring this all together. If you ever find yourself tasked with outfitting a manufacturing plant, here is your ultimate deep dive synthesis. You choose the automatic pallet changer when you are in the business of fast, lightweight mass production.
Yes.
You deploy it to completely eliminate the bottleneck of human loading time, keeping your spindle cutting metal 80% of the day.
Exactly.
But you fall back on the stationary table when you're dealing with ultra-heavy parts like ship engines, when you need the massive structural rigidity of a solid cast iron bed, and when your operation simply cannot afford the high-stress, high-cost reality of complex automation maintenance.
The invisible calculations behind how our world is built are fascinating once you know what to look for.
They really are. You now understand the intense engineering tensions that dictate how the world's most advanced factories actually survive. The next time you see the sleek aluminum body of a new electric car on the highway, or you look out the window at an airplane turbine spinning on the runway, you are going to know about the 0.005 millimeter tolerances, the risk of trapped metal chips, and the agonizing work table decisions that went into machining every single piece of that metal.
It forces you to look at the manufactured world with a lot more respect for the engineers behind it. And before we wrap up today, I want to leave you with one final thought to ponder a concept that pushes beyond the current limits of the factory floor we just explored.
Oh, I love these. Let's hear it.
We have spent this entire conversation trapped by a strict physical trade-off. You either get the blinding speed of moving parts with an APC, or you get the unyielding rigidity of stationary cast iron.
Right.
But what if the future of manufacturing doesn't force us to choose? Imagine a factory floor where we introduce a true hybrid table utilizing advanced magnetic levitation.
Wait, magnetic levitation, like a bullet train.
Exactly like that. Picture a massive metal pallet that is shuttled into the machine at lightning speed, gliding entirely on a frictionless magnetic field. But the very moment it hits position 0, the electromagnets reverse their polarity, locking that pallet down directly against a solid cast bed with thousands of pounds of magnetic force.
Oh, wow. So you get the absolute rigidity of a stationary table, but without a single moving gear.
Precisely. There are no slide rails to bend under a 10-ton load and no mechanical locking pins to ever get jammed by dirty metal chips.
Just invisible magnetic force providing both infinite speed and absolute unmoving stillness.
It would completely rewrite the rules of microscopic error and structural failure we just spent the last 20 minutes analyzing.
Magnetically flying a 10-ton block of iron into a cutting cabin and snapping it down. That is a wild image to end on, something for you to mull over until our next deep dive. Because until that magnetic levitation becomes the global standard, that insanely expensive cutting spindle is still sitting there, completely idle, just waiting for a human operator to tighten the bolts. Thanks for listening, and we'll catch you on the next one.